Today we're looking at diodes, how they work and how they're used in electronic circuitry, and particularly merge kits. But let's start with some basics and work our way up. As you can see here, they're available in the range of sizes from tiny surface mount devices up to much larger devices intended to be bolted to metal heatsinks. What are the two wires for? Well, as you can see, they're called an anode and cathode, and are designed to let the current flow in one direction only, in the direction shown by the arrow there. That's electron current we're looking at there. Conventional current flows in the direction of the arrow in the diode. But real current flows from negative to positive. Here's some of the characteristics of diodes. The maximum voltage they can handle both in forward and reverse without damage. The maximum current they contain without overheating and blowing up or degrading. The forward voltage, how much voltage you have to apply before current will actually flow through the diode. The voltage drop across the diode, and the time it takes for the current to reach a maximum when the diode begins to conduct, and the time it takes to drop to zero current when the diode stops conducting. Let's look at a very simple demonstration of it. We have a battery, a diode, and a bulb. But as you can see, because the diode is wired in that direction, no current will flow. Whereas if we reverse the diode, we now have current flowing and the bulb will illuminate. In other words, the diode will only let current flow in one direction, sometimes called asymmetric conductance. So, what are typical uses then? Let's move on. Probably the most common use you'll come across is converting AC voltages into DC voltages. Unless you're using batteries, we're going to have a mains input at 240 volts in the UK, stepping down to some lower value. And because it's alternating current, the voltage will swing above and below a 0 point in the shape of a sine wave, reaching a maximum value, dropping back to 0, reversing to a maximum in the reverse direction, going back to 0, and so on in a cyclic manner. If we now put a load on to the output of the secondary of this transformer, then the AC from the primary will be a lower value in the secondary, and of course therefore the voltage across the load is also AC. But almost all electronic circuitry is working on DC values, direct current. So AC is unsuitable, and that's where diodes come into play. If you place a diode in series with the load, then on the positive half cycle the diode will conduct, and on the negative half cycle no current will flow because it's blocked. And as you can see on the right hand side, we get what's known as half wave rectification. Only half of the waveform appears on the right hand side of the diode there. We can normally put a capacitor across the load so it gets charged in between each of the half wave pulses. The grey area you see is as the voltage slowly drops as current is taken out of the reservoir capacitor and then replenished when the next half cycle arrives. Another form of rectification uses a bridge rectifier, which essentially is just 4 normal diodes in the pattern that you see there. AC comes in as normal, but if we follow the current here, on the half cycle when this is positive and this is 0, then current will flow from the low value to the positive value along the blue line, out through the right hand side, through the load, and back in along the red path back to the AC supply. And on the next half cycle, the top connection is now at 0 volts and the bottom connection is at the higher voltage. So current will now flow from the top, the blue line, out through the load, back in the top of the red and back to the AC supply. In other words, both times of the cycle, current will flow through the load. And the result, as you see there, in both half cycles, we get current flowing through the load, and therefore we've got much more power available with what is known as full wave rectification. And again, if we wanted to, we can use smoothing capacitors, and they'll be more effective in this case because they've been recharged twice as often. Let's show it in practice. I've got a wall wart here, just feeding into a board that we can then make some tests. So let's have a look. Here is the lead coming from the transformer. We'll attach a load and we'll have a look with the oscilloscope. And as you'd expect, we've got a sine wave. However, if we replace that with a diode and a load, let's look across the load now. And as you can see, we've now got half wave rectification. However, if I put a smoothing capacitor across the load, then it charges the capacitor to give you more or less a smooth output. And that's fine as long as it's a light current being drawn. If I start to draw excessive current, however, you'll notice the pattern changes. The capacitor isn't able to store a regular DC. You're getting a hum. If I put an even greater load on it, we get an even greater variation in the output. If we replace the single diode with a bridge rectifier and we now connect the scope, we can see that we now have full wave rectification. And here we have an example of half-wave rectification in one of the pocket money kits. The yellow band shows a diode on the printed circuit board, and that particular diode there is the one which is creating half-wave rectification and then being smoothed before being supplied to the rest of that particular kit's circuitry. And that's fine because that particular kit has got a very low current draw, and therefore the charge on the smoothing capacitor is more than enough to cope with the demands. The other kit, however, for a more smooth power supply, is using a bridge rectifier and a loud smoothing capacitor. Another common and handy use of a diode is in module protection. Sometimes unkindly, although maybe accurately, described as an idiot diode. You all know that if you reverse the polarity to a module, you can easily fry the circuitry that's on that board. It's not an issue in the earlier example because we're using a filament lamp, but we still see that the lamp only lights up in one direction. Whereas if we've got a module and we fit a diode in series between the power supply and the module, then the current will only flow when you connect the power supply with the correct polarity. If you mistakenly reverse the power, nothing happens. No current will flow, but you don't damage the module. Here it is in our Merg laser detector kit. On the left you'll see the arrow pointing to where it is on the printed circuit board, and on the right hand side you'll see it's in series with the incoming power supply. If your module doesn't have one of those and there's no space to fit it, then you can fit it in series with the incoming lead, as in this example. The next example looks at the flyback diode, the diode that you'll find very commonly wired across the coil of a relay. What problem is it solving? Well, let's look. The relay has a set of switch contacts, a wire coil, and a metal armature that's able to move, pivoting at this point here. If we now apply a voltage to the coil, it creates a magnetic field. The magnetic field in turn pulls the lower part of the armature inwards and the upper part of the armature upwards, thereby changing the switching. And when we remove the power, the springs push the contacts back to the original settings. And here's where the problem comes in. You've applied current through the coil, it has created the magnetic field to make the relay operate. You remove the power, the magnetic field collapses again, and it induces a voltage in the reverse polarity across the coil. Well, that's not what we wanted. It can cause all kinds of problems. It can damage the components on the board, the various semiconductors. It may cause arcing of the contacts of the switches and can lead to interference pulses. It'll affect other circuits. So, as you can see in this Merc kit, we've placed a diode across the relay. What effect does that have? Well, when the relay energizes, no current flows through the diode because it's reverse biased. So it's got no effect on the pull-in of the relay. However, when the power is taken off the relay, we get a reverse voltage, and then in that case the diode is forward biased and can conduct current, and that prevents the current flowing through other components. The diode's properties of having forward and reverse bias are also used in this situation. Here is the Merc kit for a speed controller, and here's its circuit. It's using the LM317 adjustable voltage regulator. So normally the output from that regulator is at a lower voltage than its input, and that's fine. And we're charging up the capacitor on the output. It could be used for controlling a loco, a motor, or just as a bench variable supply. But what happens if the output became greater than the input? Well, it could destroy the regulator. How and when would that happen? Well, when you switch the power off to the input of the regulator at a time when the large reservoir capacitor is fully charged, then the output will be greater than the input, and that could damage the regulator. Or you may have back EMF from a motor that would make the output pin at a higher voltage level than the input pin. In those kind of situations, a feedback diode is connected across the input and output, and thereby, in normal circumstances, is reverse biased, but where there's a problem, it's forward biased and prevents damage. If a model railway uses DCC, then we can use diodes as train detectors to know where a loco is on any part of the layout. There's a Merc kit for this. The kit is wired in one of the legs between the command station and one of the rails. So the DCC signal has to go through the kit to get to the track. And if we isolate that section of track, we're able to detect anything that's in there. Like this. The DCC comes in, goes through two diodes and back to the track. How does that work? Well, let's start with a DCC signal. As you know, it's bipolar. It'll switch plus and then switch negative constantly. These voltages, as you see, even for small scale, are plus and minus 10 volts as a minimum, up to 24 volts as a maximum, depending on the scale you're working on. Most commonly, somewhere around plus and minus 15 volts. And these voltages are too great to directly connect to most electronic circuits. And that's where the properties of diodes can prove useful to us. Have a look at this chart of voltage against current. When the diode is forward biased, little current will flow until the voltage reaches a critical point known as the forward voltage. It's on the chart marked as VF, forward voltage. At that point, the diode is forward biased and maximum current can flow. If you increase the voltage further, it doesn't result in much extra current. And you can keep on increasing the voltage until you get to a point where you'd actually destroy the diode. But you'll notice at this point the forward voltage remains consistent regardless of the increase in current. So, for a general purpose silicon diode, the value of VF, sometimes also called the cut-in voltage, is around 0.7 volts. In fact, for all voltages greater than the forward voltage, the diode will always drop 0.7 volts across it. And that's true even with a very small current flowing through it. And we're going to take advantage of that fact. Let's look at the effect of adding one diode in series with the DCC. In the left hand side is the incoming DCC signal varying between its positive and negative polarities. The positive going half cycles are going to bring the diode into conduction, current will flow through it, and the negative half cycles will be blocked as you would expect. And on the right hand side you'll see a much diminished voltage because all we're looking at here is the 0.7 volts developed across the diode itself. The great majority of the incoming voltage is across the motor. However, with only a single diode, all the negative pulses are ignored and not passed through the load of the motor, thereby losing half the power. So we have to look at this. We now have two diodes wired in reverse parallel. That means that the DCC signal always has a way to pass through regardless of the polarity. If there's no local in that isolated section, there is no load and no current flows through the diodes. There is no voltage to feed back into the detection circuitry. However, if a local is in a track section, current will flow and the voltage pulses will be developed across the diodes. And that's true whether the local is moving or stationary, because even the small amount of current being drawn by the DCC decoder inside the local is sufficient to develop these pulses across the diodes. And the rest of the kit's circuitry detects those pulses and takes appropriate action by changing its output. Now we're almost there, but there is one more thing. You may recall that at the beginning I mentioned the turn on and turn off time of diodes. Their usual general purpose silicon diode is fine for all the purposes I've already mentioned, but their switching times are too slow for the higher frequencies that DCC use. So the MER kit uses a special type of diode known as a Schottky diode. In this case, the 1N5819 looks like a normal diode, but it's much better at handling the fast switching speeds of the DCC signal. Let's have a look at the differences. Here are two Schottky diodes back to back, and you'll notice the clean waveform, sharp rise and fall. If I replace that with two 1N4001 ordinary diodes and have a look, you'll see a marked difference there in terms of the time it takes to rise. So in conclusion, that's a number of ways that we use diodes in electronic circuits and in MER kits. There are others, but in the meantime, are any questions or comments or suggestions?